Hi guys, welcome to my channel where we all hate J so that we just crack it and execute the matrix. Today it's a question from one of the hardest questions from Pathfinder. It's Pathfinder waves and oscillation, and it's a challenge your understanding number 2. I will bring one video on the challenge your understanding number 1 too, but for this let me first focus on this question. This is a very hard question according to me because I must say hard, I will say conceptual, it's a polyconceptual problem. Let me just read the question first. So what's the question, sir? It's a block of mass M placed on a horizontal conveyor belt is attached at one end of a spring of force constant K. So this is K. You can see the other end of the spring is attached to a support. Coefficients of static and kinetic friction between the belt and the block are mu s and mu k. Initially, the belt, the block, and the support all are moving toward. That means this whole thing is moving with it, okay, with constant speed u. Now they said now what happens? Uh, Initially they built, okay, so the support is suddenly stopped. So this is the part, main question part here. The support is suddenly, so you stop it by some external mechanism, you just stop it. And you have to explain qualitatively the mechanism of motion of the block after the support is stopped. As the first question, find the maximum and minimum deformation of the spring, and as said, to find period T of the oscillatory motion of the block. Okay, so I think so. Let me start the question. So let me first tell you how the first part of the question. How what is the mechanism of motion of the block after the support is stopped? Okay, so if I show you, just suppose this was a block. Okay, so when the support was suddenly stopped, and there was a friction working with it. Correct. Yeah, of course, there was a friction working with it that was causing to move with this conveyor. Now, what happens when it suddenly stops this fixed? Now the block starts to move away from this. Means that the spring starts deforming, right? And when the spring starts deforming, the spring force increases quite fast. At first it was zero, then it starts to increase and it becomes kx. But then at a point, does the velocity of the block change? The question is, the answer is no, because there is a certain friction value, that is mu s mg. What is the maximum friction that can work on the body? So until your spring force is equal to that, till that you cannot say that the block, the velocity of the block will change. Okay, so let me just clear the first part, that when I just suddenly stop the support, then the block starts moving. A block keeps on moving with velocity u, because the maximum friction is mu s mg, and at first spring force is spring force is zero. At first there was no deformation, right? X deformed is equal to zero. There was no deformation. That's why spring force was zero, and there was sufficient friction that the friction will work up to a point until this kx this means the spring force exceeds the maximum friction. Up to that point, friction will work according to it, right? Friction will work on its own. Am I correct? So let me move on to the next part of the question. So uh, in the next part, let me see what's it's written. Okay, so this is just written that thing that this is the thing that Fs and there is friction. So until the final phase comes, this was the scenario. F was Fs, and that's why it just keeps on moving with you. There was not a problem. Then it becomes M is equal to Fs, right? When finally the friction with the spring force becomes equal, and after that it starts deforming, and after that the friction force suddenly decrease. I'm just so listen to my words carefully. The friction force suddenly decreased to M mu K. मतलब M mu K. That is kinetic friction coefficient. m mu kg by m mu kg. That will be the sudden decreased force. This is with the suddenly because the force suddenly decreases, right? So what will happen after that? When it suddenly happens, suddenly decreases, you can see there was the block and there was a friction force that was mu s m g, and then it suddenly decreased and friction force was equal to, and then suddenly what happens? Sorry. Then suddenly there is the friction force and it becomes mu k mg. Actually, I cannot say it's mu k mg. Now, it's clearly the kinetic friction coefficient is less than the static friction coefficient. That's why you can see that there is a net force towards the main position or towards the support. Can you say that? Yes. So, uh, this is a concept that when the spring force touches, is equal to the maximum friction that can be applied to the block. After that, the friction, at that point only, the friction just steeply decreases to mu k mg. So you have to carefully listen to this part because this is where the entire complication of this question remains. So after that, what happens? So let me just advance in this question. So after that, you have your dx as mu, right? You have your dx is u, and you get a equation here. What happens? There is your block. There is u. It is going with u. There is a fixture. There is this thing. There's the spring force, right? There's the spring force, and your friction is working at there. Now you may ask, how am I doing that the friction is working there in this side? Sorry. How am I ensure that the friction is working towards the velocity? So listen to me carefully. At that point, when the friction directly means there was the Fs and it becomes mu k mg. Can you see there is a net force towards there, and there's a u velocity towards there. So can you just say to me that after this point, what will be the effect on u? Will it decrease? Will it try to decrease or will it increase? The answer is of course it will try to decrease. Now you may ask why? Because see dx dt is u, right? Dx dt is u, and your and u is towards the u is away from the support, and your dx dt is o, and your net force is directed anti-parallel to your velocity u, right? Your u is towards this direction and your net force is this direction. So as you can see, the conveyor belt is moving with u velocity. So if there is a relative velocity of the block with the conveyor belt, only then friction will work then only friction will work, right? So this is moving with u and this is moving with less speed. So this is moving with a speed which is less than u. Then the friction will try to increase its speed and it will work towards the forward direction. Can you understand my what I'm saying? Because as the block is moving toward away from the support, but the net force is trying to decrease its velocity away from the support. But the conveyor belt is having velocity u. That's why the friction will try to increase its velocity. You know that friction try. What does kinetic friction do? Kinetic friction just tries to oppose the motion, the relative motion of the body. So what is the friction do? Friction will work to away from the support so that to increase your velocity and make u. As far as the question is concerned, I hope you have understood this part. Okay. So you have to now I'll form a differential equation like to govern the motion. Right. So let me start. So now you can say this. Follow this diagram. You can see just a minute. You can see that m d square x dt square. That means m a, the acceleration. I am taking x as this direction, is equal to uh, okay. So this okay. So just a minute. It is first. Let me just govern this direction because this will come later. Okay. So first, let me just do this thing. What is there to it? I mean, so you have m d squared x dt squared. I mean, you can see actually why I stumbled there because there is said dsdt is greater than u, but in this thing the dsdt is less than u. This is also what I'll explain. So ma is equal to the friction is working towards x, right? Friction, you can see the friction is working towards it, so it is increasing it. So plus m mu kg, that's kinetic friction coefficient mu kg, minus k into, now you may ask why I have chosen this, m mu kg by k plus x. I hope you can see that when the block is moving, right? When the block is moving, where does its mean position lie? You may argue that its main position lies on mu s mg by k, because from there it started having velocity u, right? But that is a limiting case. That is an exceptional case. Why? Because there is a, suppose there is no kinetic, there is no static friction at all. Suppose kinetic friction and static friction are same. Then what will happen? Then the main position will occur at m, where the kinetic friction will be equal to the spring force. That is the x deformed. What will be? That is kx will be equal to m mu kg by mu kg. So that is x, where your that is the mean position. That is your mean position, and from there it will deform by x. This is not its mean position, but why this is not your mean position? Because when the block is like at the first case, when I am when I'm just releasing the block, I'm just holding the support. The is block starts deforming its velocity. After that deformation, it is correct that mu s mg by k. After this deformation, the block starts deteriorating its velocity. But think of it when if there is nothing, this is a something. I mean, mu is mg by k. It's only working at that place where the relative velocity is not zero. But in general case, where there will be the velocity when suppose this block goes there and this comes here, right? This comes here completely. In that case, there is no place of the static friction. There is always be a kinetic friction. Now, kinetic friction will be equal to the kx only when the x is mu k mg by k. That's why that's the main position. Understood? Okay. So the next thing, it's m d squared x dt square is equal to m mu kg minus k into m mu kg by k plus x. But there is a caution when dx dt is less than u. Of course, that is correct. Why this is correct? Because suppose this block is having velocity more than u. It's having velocity more than u. Suppose the block is having velocity more than u plus something, and the conveyor belt is having u. So what will the friction do? Friction will try to reduce its speed and make equal to u, right? But when the velocity is less than u, the friction will work towards that thing and it will try to increase its speed. This is very important while forming this differential equation. Now I have found another differential equation which is correct. That I have found another differential equation. Okay, I have found it, but this is correct also, that when density is greater than u, there will be m mu kg will act towards it will work against the velocity and it will give these things. Okay, but this part is not needed in this question. I'll tell you why, but this part is not needed in this question. Okay, I will move to the next part of the question. So now, what will happen? Suppose the block has moved to this is the x1. What is x1? This x1. Okay, so this image is slightly misrepresenting. I will just delete this image. I will draw image for you. There is the block, and the block is moving towards this. This is the mean position. Suppose here it is having a velocity u. Yes, it's decreasing, but it's having the velocity u now. So it will move towards something. It will move like if this is x mean. This is the x2. Suppose x2. This is the mean position. This is x mean. This is x2. The block will move. Not only there. This position is what? This position is x2 is mu s mg by k. From where the block starts deforming its velocity. But it is not the maximum deformation. The maximum deformation will be more than this because the box will go more because it has a velocity here. So I can use work energy theorem to find what will be the maximum deformation. So here the block is having half mu square, right? The kinetic energy. So I can say the kinetic energy. This is the kinetic energy. This is the spring energy. This is already deformed mu. This is mu. The total deformation is mu s mg by k at this position, right? So this will be half. This will be the spring potential energy, right? And when it finally goes at max deformation, the u will be 0. So that's what defines why that is the max deformation. At max deformation, it will be there will be only spring potential energy. This is initial, this is final. So, and yes, of course, I missed that part, of course. And this whole thing will be equal to the work done. Change in mechanical. This is written as change in mechanical energy. Okay, you can see. I think this is the kinetic. This is the initial kinetic energy. This is the initial potential energy, and this is the final potential energy. So this whole thing, the change in potential energy is equal to the work done by the force. Now, where is the force? What force is working this thing? What is there to work? There is this friction, which is working towards the thing. So that you can see the friction is working. This is x max, and this is mu s mg by k. Then the friction is Fs. The work done by friction would be Fs into x max minus mu s mg by k. Right, that's what it is written here. You can see. And now you just solve this. You just solve this thing, and you just do it, and you get x max as this. You understand? You get x max as this. Okay. Now the question has also asked what is the x minimum. Now let's see how to find that x minimum. Suppose this is the reference point. Of course, this is the support. This is x minimum, and this is x maximum. And you just try to just do the energy conservation between these 2 points. What will happen? Half k x max square. Now this part I have to explain, of course. So can you see that when the block was here, it is having a speed u, then it start decreasing. The velocity is decreasing, it decrease. There comes the final thing, then the velocity reverses, right? And all this period, when x minimum also occurs, the velocity again becomes zero, and all those things and all the way to the x minimum, does anyone the velocity becomes plus u? No. That's why all the time the friction only works towards this, because if the friction is not working towards this, because the relative motion, the conveyor belt is going towards with u velocity, and the block is moving towards this. So of course the friction will work for you, because it will tries to reduce the relative motion. I hope you understood. So the friction will always work this towards the when if the block comes from x max to x minimum. So friction is doing negative work, right? So minus mu k mg, and what is the work total? This is the x max and this is the x min. So x max minus x minimum is equal to half k x into min square. You can see this is the so work per energy theory I'm using, and I get x minimum as this. Okay, so this is the first and second part of the question. The first part is not completely described. Now let me listen to this carefully. Okay, there is the support stop. There is the spring. It was t equal to 0. Then the block becomes this. It is t equal to t1 when this thing is okay. But still of course friction is more than this, because friction was in auto adjusting mode. Then what happens? Then after a certain time, friction goes to the block goes to this. Okay, just wait. Here is and it is mu s mg by 2. After that, the block will go towards this is x max. Then the block will come towards this is something x min. This is x min. Then the block starts going towards this thing, and when the velocity reverses towards this, there comes a time when the velocity is again u. Will you agree to me? There is a time when the velocity is again u. But then can you see that the friction becomes static again? Yes, at this point, x1 suppose, this point the friction becomes static again. How can you say that the friction becomes static again? Because there is a spring force, and you can say by this thing that in this motion the friction force will be less than mu s mg. And as it becomes u again, that's why at this part the friction is again static. The friction will be again static. Okay, so now you understand how is the motion. The motion is actually like pretty like this. The motion is that the block, if you draw the whole thing, this is x min, this is x1, this is x2, this is x max. So the block goes from here to all the way here, to all the way here. This part is SHM, because it follows the SHM equation. Then this part is this is as surprised. I was surprised by the beauty of this question as much you are. Of course, there is the SHM part is this, and this part is constant velocity. This is a very, very important part of this question. You have to just understand it. That means you are just suppose this is a phasor diagram. Suppose it is a phasor, and the SHM part you are doing all the thing you are doing SHM, and then this part you are just removing from that SHM, and all the other part that is doing SHM, and this part you just remove from it. This is how the mechanism of the block. So I answered the question A. Now the question is that find the time period, right? So as I told you that the block is performing SHM in this position from this to this. Now if I complete the whole SHM, if I am completing the whole SHM, then I can say that at x2 position it is having a velocity u. If I am completing the whole SHM, then what I will say? I will say I will write the SHM equation that x max minus x minimum. That means from the x minimum, of course, as that was our origin, not the x minimum. So this will be equal to oh, so this is the amplitude. Sorry. This is the amplitude. Of course, this is the amplitude because x max minus x minimum is the amplitude. So amplitude into sine of omega t plus 5. Okay. So this is our SHM equation. Now x max minus x minimum into sine phi at t equal to 0. I just do this. X max minus x minimum into sine phi is equal to mg by k into mu s minus mu k. That is the deformation. That is the deformation. This is m mu k g by k, and this is m mu s g by k. Right? So what will be so I to find the phase angle I do this, but phi is equal to mg by k into mu s minus mu k, and by the calculation you can do just this, that phi is equal to tan inverse of this. Okay. So this is the phi, and what is the and the SHM part, you know that until it goes to the phi phase, means if this is a phasor and this is phi, so you just cancel this part, and this is the what all happens, and then again you just cancel these two part. Yes, you just remove this part from the SHM. So the time period of the SHM part of the motion will be this, and time period of the linear part of the motion, that means the distance between x2 minus x1, that is nothing but mu s mg, as you can say mu s mg minus mu k mg by ku. This is the linear part by u, of course the distance by velocity, and you get the time period as this. This is a very beautiful question. I mean, this is just a spectacular question of SHM, and one of the hard, well, not one of the, I think probably the hardest question of SHM. So I just laughed how they think how the question was made. So that's it, guys, and please like, share, and subscribe to my channel. If you don't understand any part of it, please write in the comment section. I will of course answer them. Because if I cannot answer it by writing, I'll probably give you a drive link where I'll upload the video and you can see the video, clear your doubt.